Welcome back to this advanced manufacturing and process modeling course. So, we were discussing about the forging module of this course. So, we have already discussed about uniaxial compression based forging and the mechanics involved in it. So, today we will start with establishing the advantages and disadvantages of the forging process, and we will move on. So, advantages of forging. So, forged parts possess high ductility and offers great resistance to impact and fatigue loads. So, forging refines the structure of the metal. It results in considerable saving in time, labor and material as compared to the production of similar item by cutting from a solid stock and then shaping it. So, forging, if properly planned, can also serve as a near net shape manufacturing process, such as in case of metal casting and powder metallurgy. So, it is also possible in case of forging. So, forging distorts the previously created unidirectional fiber as created by rolling and increases the strength by setting the direction of the grains. So, this is also the reason that the directional flow of grains, so that it has got it offers improved properties, improved directional properties compared to the same material which is developed by melting casting route. So, because of intense working, flaws are rarely found, so have good reliability and forged parts can be easily welded. So, these are the advantages of forging processes, and disadvantages are so rapid oxidation in forging of metal surface at high temperature results in scaling and which wears the dies. So, the close tolerances in forging operations are often difficult to maintain, and so forging is limited to simple shapes and has limitation for parts having undercuts, etc. So, and also some materials are not readily worked by forging because they do not possess the much needed formability which is very much required for metal forming forging processes. So, the initial and the other disadvantages are the initial cost of forging dies and the cost of their maintenance, which is relatively high, and the metal gets cracked or distorted if worked below a specified temperature limit. So, that is another disadvantage of forging process. So, following that we will discuss about rolling. So, rolling is a versatile forging process where the goal is to plastically deform the work plate to achieve the required dimension. So, it can be based on the temperature of the workpiece, it can be classified as hot rolling and cold rolling. So, in case of hot rolling, the temperature the workpiece is basically processed at a temperature higher than its recrystallization temperature. So, that means the rolling temperature Tr is higher than the recrystallization temperature of the particular metal, and in case of cold rolling, the rolling temperature is lesser than the recrystallization temperature of the metal involved. So, this is the criteria for hot rolling, and this is the criteria for cold rolling. And so there is a question that how hot is hot and how cold is cold in case of rolling. So, if the temperature is above room temperature, however, it is well below the recrystallization temperature, so then we call it as cold rolling. However, when the temperature is below recrystallization temperature, but well above the room temperature, then we introduce a rolling process which is in between the hot and cold rolling, which is termed as warm rolling process. So, so these are the broad classification of the rolling process. So, it involves plastic deformation of metal by passing it between the rolls, widely used for high production and precision control, and the forces high compressive stresses and surface shear stresses acts on the metal due to roll pressure and friction, and the frictions role. So, frictional forces are crucial in drawing metal into the rolls for deformation. So, this is the so and these are the different shapes that generally being produced by rolling process. Mostly they are hot rolled, starting from bloom to structural shape, and also this is the railroad, I mean this rails that is shown over here, and also I mean when there is I mean high mechanical property is on demand, then there are applications where cold rolling also finds suitably. For example, in case of sheet metal forming, and so also in case of storage racks used in heavy duty industries, where for assembly operation individual components are kept in the storage racks, which are so there, I mean those are also built with this cold rolled steel. So these are some as application of the hot rolling and cold rolling. So so with this we are moving. So the components of a rolling mill, so it includes rolls, bearings, housing, and a drive system to apply power and control roll speed. And forces in rolling, so rolling forces can reach several meganewton, requiring highly rigid construction and large motors for operation. Investment and design, so modern rolling mills require significant capital investment and extensive engineering design due to the complexity and scale of the operation. And the type of rolling mills, so rolling mills are classified based on arrangement of the rolls in the mill. So with the simplest being the two high mill, where rolls rotate in one direction, and two high reversing mill, it enhances productivity by allowing work to pass back and forth through the rolls by reversing the direction of rotation. So these are the basic concepts for rolling. And then now if we discuss about three high mill, so it consists of a upper and lower driven rolls with a middle roll rotated by friction, allowing continuous rolling. So this is a typical example of a three high roll. So you can see that so basically for the smaller roll, which is the work roll, there is a backup roll present. So because otherwise it may not be able to sustain the the deformation forces, strains generated in the workpiece, and they may get dislodged, and also they may experience failure. So that is why it is the role of this backup rolls is extremely important in this case. So small diameter rolls, so it reduces power requirements for rolling, but needs support from larger backup rolls due to reduced strength and rigidity. And four high rolls, four high mill, so it features small diameter work rolls supported by large backup rolls, ideal for rolling thin sheets to precise tolerances. And then the cluster and Saint-Jimmy mills, so cluster mills have work rolls supported by two backup rolls, with Saint-Jimmy mills being a specialized version for rolling thin high strength alloy sheets or foils. So we will see different kind of rolling mills in this slide. So this is a typical example of tandem rolling mill. So multiple rolling stands operate in sequence. So so this is a stand 1, and this is stand 2, stand 3 and 4. So you can understand from here that from this uncoiler the thickness is, say if it is the initial thickness is Ti and the final thickness of the rolled part is say Tf. So then so here Ti is significantly higher than much higher than the final thickness Tf, and this much thickness reduction could be achieved with the advent of a tandem rolling mill at one go. So that means that from the uncoiler to the wind up reel, the whole deformation process can be executed with the help of a tandem rolling mills at one go. And then the case of tension control, so the uncoiler and wind up reel maintain back and front tension, improving strip handling and product quality. And here this schematic shows the typical examples of two high rolls, where the two rollers which are placed at the top and bottom of the workpiece are involved, and then there are two high reversing mills are also shown. So in this case what happens that the roller change direction. So once it is rotating in the anti-clockwise direction, clockwise, then it also gets reversed to the clockwise direction, so that the total thickness reduction that is necessary for the workpiece can be achieved by back and forth feeding of the workpiece in between the rolls. in some subsequent passes. And then this is the typical example of a 3 high roll. So, you can see that. So, this is a typical case where the rolling the deformation thickness reduction of the workpiece can be achieved at in a tandem process. So, what is the case here? So, the workpiece which is going out from these two rolls, say roll number 1 and roll number 2, it then fades between the roll number 2 and roll number 3, and this is how the necessary thickness reduction in the workpiece can be achieved. So, so this is another example of a 3 high roll. So, where it is, you can see the backup rolls are much smaller in diameter. So, which requires much lesser power, whereas to offer the required strength and rigidity to these small working rolls, 2 backup rolls are kept over here. So, this is a typical case of 3 high roll, and then this is a case of this is the case of 4 high roll, and then this is E. So, that is the cluster mill. So, you can see the interesting concept here is that for each roll there are 2 backup rolls. So, if I number the top working roll as 1, so you can see that there are 2 backup rolls, 2 and 3 for the top working roll, and even for the backup roll 2, you can see there are 2 further backup rolls. You can term it as 4 and 5, and similarly for 3 it is 5 and 6. So, this is how the cluster rolling mill works, and we can achieve significantly higher thickness reduction because the work rolls are supported by multiple backup rolls in this case. So, then here comes the concept of hot rolling, which involves deformation above the recrystallization temperature between 0.5 Tm to 0.75 Tm. So, advantages are significant plastic deformation can be given to the sample, significant change in workpiece shape can be achieved, lower forces are required, materials with premature failure can be hot formed, absence of strengthening due to hot work hardening. So, because here the in case of cold working, dislocation glide becomes dominant deformation mechanism, whereas in case of hot rolling that this work hardening or this strengthening due to dislocation pile up does not happen, because plastic flow becomes easier because of the because it becomes the temperature assisted flow of the matter. So, hence the work hardening is not involved in case of hot rolling, and this is also the reason that the mechanical strength that we get in case of hot rolling is much lesser than what we can get for the same material in case of cold rolling. And another reason is also in terms of the microstructure, because in case of hot rolling the recrystallization happens because the workpiece is being worked at a temperature higher than its recrystallization temperature, which is not the case in case of cold rolling. So, so there is a preferential texture evolves in case of cold rolling, which is not the case in case of hot rolling. So, these are basically the differences, and however, the prime advantage of hot rolling is that much higher deformation can be imparted to otherwise to the materials which are otherwise difficult to be deformed under cold rolling conditions. However, the disadvantages are shorter tool life and poor surface finish, lower dimensional accuracy and sample surface oxidation. So, these are the disadvantages in case of hot rolling process. So, now we are moving to the cold rolling process. So, cold rolling process produces sheet and strip with superior surface finish and precise dimensional tolerances, and it results in strain hardening, increasing material strength. So, comparison with hot rolling. So, cold rolling offers better surface quality than hot rolled products, and more non-ferrous metals are cold rolled compared to steel products. So, because in case of non-ferrous metals, the rolling force requirement is still lesser, much lesser, although the cold rolling requires much higher rolling force compared to hot rolling. However, in case of non-ferrous metals, it is still within a certain limit. However, in case of steel, it is much higher. So, hence cold rolling is popular in case of non-ferrous metals. So, and also because of their widespread usage in the sheet metal form in case of non-ferrous metals, also facilitates higher usage of the cold rolling technique in case of non-ferrous metals. So, the starting material cold rolled steel sheet begins with pickled hot rolled coils from continuous hot strip mills, and for non-ferrous sheets hot rolled strip or cast material in case of copper alloy is used as a starting material. So, the operating conditions cold rolling is typically performed at or slightly above room temperature, but of course, well below recrystallization temperature as discussed earlier. So, so the advantages of cold rolling compared to hot rolling are it can meet closer dimensional tolerances, it offers good surface finish, and because of strain hardening higher strength and hardness can be obtained in the cold rolled part, and the grain flow during deformation provides the opportunity for desirable directional properties. So, this is an important thing. So, that is not at all possible in case of hot rolling, which is effectively can be achieved in case of cold rolling processes. So, since no heating of the workpiece is involved in case of cold rolling, furnace, fuel, electricity costs are minimized in this case. So, machining requirements are minimum, resulting in possibility of near net shaped forming in case of cold rolling. Okay. So, the disadvantages compared to hot rolling are it needs higher forces and power, strain hardening of the work metal limit the amount of forming that can be done. Sometimes cold forming, annealing, cold forming cycle should be followed. So, this is a important thing to be considered here. So, often it becomes impossible to impart the required level of strain that is necessary in the in cold rolling to achieve the desired thickness reduction at one go. So, of course, there are multiple passes need to be done over the workpiece to achieve that thickness reduction, and moreover after a certain number of passes the material gets so much work hardened that further plastic deformation, imparting further plastic deformation by cold rolling route can cause catastrophic failure to the workpiece, and to avoid that it is recommended to go for intermediate annealing and then thereafter the cold rolling can be done again. So, that is a remedy, that is also the disadvantages compared to hot rolling. So, because in case of hot rolling because the workpiece is maintained at high temperature, so there is no need for periodic heating. So, you can say that compared to hot rolling, cold rolling is a intermittent process because of the need of intermittent annealing involved, and the workpiece is not ductile enough to be cold worked. So, this is again a disadvantage. So, further cold working may not be possible in the already cold worked cold rolled workpiece. Okay. So, now we will try to understand the mechanics involved in the rolling process. So, the differential equation for the equilibrium of an element of material being deformed between two high rolls is common to all the theories of rolling. So, the derivation given below is based on the following assumptions. So, what are the assumptions? The arc of contact is circular. So, here we are talking about this arc of contact. So, which is circular, no elastic deformation of the rolls. So, rolls are perfect rigid bodies, and hence no elastic deformation of rolls are possible. So, and then the coefficient of friction is constant at all points on the arc of contact, and so the mu is constant here throughout the arc of contact, and there is no lateral spread. So, that means the workpiece is only experiencing thickness reduction and analogous increase in length, and there is no change in the width direction. So, that is why the problem can be considered as a plane strain problem, and then it can be treated accordingly, and plane vertical sections remain plane. So, that is the deformation is homogeneous. The peripheral velocity of the rolls is constant, that is another assumption. The elastic deformation of the sheet is negligible in comparison with its plastic deformation. And finally, the distortion energy criteria of yielding for plane strain holds good in this case. So, what is the criteria, distortion energy criteria? It is considering the maximum and minimum principal stress, which is sigma 1 and sigma 3. So, sigma 1 minus sigma 3 is equal to 2 by root 3 sigma 0. Sigma 0 is the ys of the material which is undergoing rolling here, and then so it becomes equal to sigma 0 prime. So this is what, and this schematic shows the initial thickness H0 to the final thickness or height of the workpiece which is undergoing rolling process, and this is a infinitesimal element considered along the under the angle of arc of contact. So so here which is where at any location within the arc of contact, the height of the workpiece undergoing rolling is termed as small h. Okay, and this is a typical free body diagram which shows the several forces acting in the rolling process and their direction. Okay, so let us move on. So to understand the mechanics involved, so the stresses in the rolling process. So radial pressure PR, so which is termed over here. So this is basically the radial pressure PR. So which is acting at a tangent tangential mode compared to the workpiece. So hence it needs to be resolved into vertical and horizontal components. So the angle between the tangent direction of the rolling pressure and the perpendicular line over the from the this region of application or the point of application of the radial pressure is theta. So hence the rolling pressure PR can be resolved in the vertical direction as PR cos theta, and in the horizontal direction, that means in the rolling direction, as PR sin theta, which is shown over here. Okay. So and then radial pressure acts perpendicular to the strip at contact point. So tangential shear stress is tau is equal to mu PR. Mu is the coefficient of friction here, which acts along the contact surface proportional to radial pressure and friction coefficient mu. And the stress components, the stresses are resolved into horizontal and vertical components, and horizontal component of radial stress here is so PR into r sin theta d theta. Okay, because we are talking about a small r d theta strip from the total arc of contact. So here so this is the tangential so the horizontal component of the radial stress, and the tangential friction force is mu PR r d theta. So its horizontal component is mu PR cos theta into d theta. So uniformly distributed stress sigma x acts over the vertical faces of the element. So the summation of horizontal forces critical for determining the equilibrium conditions in the rolling. So sigma x plus d sigma x into h plus dh plus 2 mu PR capital R cos theta d theta minus sigma x h. Okay. So basically, so this is the direction. So we are basically trying to establish the equilibration of forces at this reference point. So then minus sigma x h minus 2 mu PR capital R sin theta d theta. Okay. So because we already know the horizontal component of the radial pressure, that is also the rolling direction. So that is PR sin theta, and why there is 2, because we are talking about 2 rolls over here. So it needs to be multiplied by 2. So that is why 2 PR r sin theta d theta, and simultaneously the frictional due to the friction force, the reaction force of the radial pressure, that is mu PR. So here also, so the horizontal component is mu PR cos theta. So the mu PR cos theta, mu PR into capital R cos theta d theta, here again it is multiplied by 2 because we are talking about 2 high roll. So then after simplification of this expression, we are getting as d sigma x by dx is equal to 2 PR r sin theta plus minus mu cos theta. Okay. So so here so the there is significance to this plus and minus sign. So so the friction, so when it is positive, so the positive signs applies between the exit plane and the neutral point. So neutral point in case of rolling is applied somewhere over here. So, that means at the middle of the arc of contact. So, hence I mean so this positive sign applies between the exit plane, the direction where the workpiece is exiting, and the neutral point, and the negative sign applies between the entrance plane and the neutral point, and the signs arise due to the change in friction force direction at the neutral point. So, this principle is based on the von Karman equation named after its originator. And the vertical force equilibrium. So, forces acting vertically are balanced by specific roll pressure, and the equilibrium in vertical forces leads to a relationship between normal pressure and radial pressure. So, P is equal to P r into 1 plus minus mu tan theta. So, this is the relationship between the radial pressure and normal pressure in case of rolling. So, the relationship between the normal pressure and the horizontal compressive stress sigma x is given by the distortion energy criteria of yielding for plane strain. So, which is again equal to sigma 1 minus sigma 3, there is a typo, is equal to 2 by root 3 sigma 0, that is sigma 0 prime. So, here sigma 3 so here the higher dominant of the principal stress is the normal pressure that is exerted in the workpiece by the roller. So, then this is so sigma 1 is P and sigma 3 is the sigma x, that is the the compressive stress is generated because of the rolling pressure on the workpiece. So, then P minus sigma x is equal to sigma 0 prime. So, here P is the greater between the two compressive principal stresses. So, then as per Bland and Ford provided a simplification for rolling problem. So, the simplification applies to cold rolling under low friction conditions, which is valid for contact angles less than 6 degree. So, according to lesser contact angles, so we can approximate sin theta as theta and cos theta as so because the theta is very less, so theta it is close to 0. So, that is why we can approximate cos theta as 1. Okay. So, then so we can write here that d d theta of sigma x prime h is equal to 2 p r r prime into theta plus minus mu. So, it is also assumed that P is equivalent to the radial pressure, that is normal pressure is equivalent to the radial pressure P r. So, the above equation can also be simplified and sigma x is equal to P r minus sigma 0 prime. So, we herefrom we know that from this equation we can estimate that sigma x is equal to P minus sigma 0 prime, and because we are assuming P equivalent to P r, that is radial pressure. So, we can also write P r minus sigma 0 prime is equal to sigma x. So, that is what is written over here. So, so by substituting this expression into the equation and integrating this expression in the top so into it here and then integrating it, so relatively simple equations for the radial pressure can be obtained. So, for from roll entrance to the neutral point, the radial pressure is following this mathematical expression, that is P r is equal to sigma 0 prime into h, that is height at any given location of the workpiece within the length of arc of contact between the rolls divided by h 0, that is the initial height of the workpiece, that is h 0. It can also be termed as h initial into 1 minus x b sigma x b by sigma 0 1 prime into e to the power mu h 1 minus h. So, here and also the mathematical expression for the rolling pressure for the region from neutral point to the exit plane roll exit is P r is equal to sigma 0 prime into small h by h f 1 minus sigma x f by sigma 0 2 prime into e to the power mu h, where h capital H is equal to 2 into r prime by h f to the power half tan inverse r prime by h f to the power half into theta. So, here the sigma x b is the back tension involved in the applicable over the workpiece, and sigma x f is the front tension being applied over the workpiece. So, the pressure distribution in rolling. So, here subscript 1 refers to quantities evaluated at the roll entrance plane, and subscript 2 refers to quantities evaluated at the roll exit planes, and the pressure distribution is calculated using specific equations over the arc of contact between the rolls. So, rolling load P, so the total force or rolling load P is the integral of the specific roll pressure over the arc of contact. So, that means P is equal to R prime into B, integration 0 to theta is equal to alpha, that is contact angle. So, integration P d theta. So, where small b is the width of the sheet, which is as told at the beginning, that width is not changing, that is why the problem is treated as a plane strain problem. So, it is only changing the height, the rolling process is changing the height, and accordingly it is changing the length of the length of the workpiece. So, here B is the width of the sheet and alpha is the contact angle, and this is the expression to estimate the rolling load. And so, the sticking friction, so in case of sticking friction, strain rate for hot rolling with sticking friction is given by this expression, that is epsilon dot is equal to V by H is equal to 2 V r sin theta by H, which is again equal to can be simplified further as 2 V r sin theta by H f plus d 1 minus cos theta. So, the maximum strain rate occurs near the entrance to the rolls. Thin sheets undergo higher strain rates than thick slabs under equal percentage reduction, and the mean strain rate. So, with sticking friction, the mean strain rate is given by epsilon dot is equal to V r into 1 by r delta H ln H 0 by H f, where V r is equal to 2 pi n and n is the rolls revolutions per second. And then the slipping friction. So, at the neutral point, surface velocity of the metal matches the rolls peripheral velocity. So, the strain rate for slipping friction epsilon dot is equal to 2 V r H n cos beta tan theta by H f plus d into 1 minus cos theta whole square. So, 1 minus cos theta whole square. So, metal thickness at the neutral point is given here as H n, and theta and beta are geometric parameters influencing the strain rate. So, so this is the strain rates expressions for sticking friction and slipping friction is introduced over here. So, sticking friction happens at the neutral point and up to a certain distance from the neutral point, whereas slipping friction is exists from which starts from a certain distance from neutral point, and then it is established till the end of the workpiece, till the exit of the workpiece, and also up to the entry of the workpiece. So, the region where the slipping friction is valid is much wider than the region where so the region where slipping friction is valid is much wider than the region of sticking friction. So, with this we are we will discuss about rolling load and torque in hot rolling. We can discuss in the next class about that. So, for this class we are stopping here. Thank you.